Hello friends, welcome you all. In today's video, we will discuss another variant of finite automata that provides some output. In all earlier videos, we have seen all FA that we have discussed. They are known as finite automata without output. Why without output? Because they are providing only the binary output, either the 0, 1 or valid, invalid, yes, no. These kind of outputs are given by all these finite automata. So they are known as finite automata without output, or whatever they are giving as output, it is fixed for all input. Whatever your input is, and their output is never changing. It may be yes or no, valid or invalid, 0 or 1. So binary kind of output is there. So they are considered as finite automata without output. But in this lecture, we will discuss one more class of finite automata that provides output. So if you give any input to the these kind of finite automata, so the output would be depend on your input provided. So if your input is longer, having more number of symbols, so in output you will also get a longer string. But if your input is shorter, so your output will also be shorter. So these kind of finite automata are known as finite automata with output. So in this category, my friends, we will discuss two types of finite automata. There are two categories of these kind of finite automata, and both these categories are named after their creator. So first is Mealy Machine. First is Moore machine, that is known as Moore machine, and the creator of this machine is E.F. Murray. E.F. Murray, that was first created by E.F. Murray. So after his name, this machine is known as Moore machine. And this another variant of this kind of finite automata is Mealy machine. And this was first introduced by George H. Mealy. So it was first introduced by George H. Mealy. So after his name, it is known as Mealy machine. So these two kinds of Moore and Mealy machine we will discuss as finite automata with output. So in next couple of lectures, we will discuss both these machines in detail. Now, we will start with Moore machine here. So friends, as we discussed, Moore machine is finite automata with output. So now we will discuss the mathematical definition of this machine. So earlier, whatever finite automata we have discussed, all we have 5 tuple machine. But as you can see here, friends, and this is 6 tuple machine. This is 6 tuple machine. And what these different tuples are, so you can see Q is again the set of all possible states of the machine. Then sigma is set of all input symbols of the machine. These two are same as finite automata without output. And then delta. Delta is set of C. There are two delta we are using. This in Greek letters, this is known as uppercase delta, and this is known as lowercase delta. So memorize the symbol. Remember the symbol, friends. So this triangular shape symbol is used to represent all output symbol of the machine. Like sigma is all set of all input symbol of the machine. So this delta is set of all output symbols of the machine. Then a small delta is the transition function, that is same as finite automata without output. And then one more function we have added here, that is lambda. So lambda is known as your output function, and Q0 is same as finite automata without output. So it is initial state of the machine. So now Moore and Mealy, both machines are 6 tuple machine, and only the slight difference is there in output function. So in both these machine, the 6 tuples are same. So friends, we will discuss now the transition function and output function of this machine and how these are mapped. So let's see. So transition function in this machine also, in Mealy and Murray machine also, or you can say in finite automata with output also, we see we changes the state based on the current state and current input symbol. So again, the transition function would be of same kind. Q cross sigma gives Q. Q cross sigma gives Q. Remember, friends, this is deterministic machine. This is deterministic machine. Both these Mealy and Murray machines are deterministic. So they will always have this kind of transition function. So Q, we will see the present state, we will see the present input, and based on the combination of these two, we will move to the next state. Now, this is the transition function, and now output function we will discuss. So, see, friends, in Murray machine, with each state, in Murray machine, with each state, one output symbol is associated. In each with each state, one output symbol is associated. So, this particular machine, the output function for this machine would be Q is directly mapped to delta. Q is directly mapped to delta. As I told you, with each of the state, one output symbol is associated. So this is the output function of Murray machine. This is the output function of Murray machine. And now I will take one example of Murray machine, so it will be more clear to you. So friends, this is one example of Murray machine. As you can see here, with each of the state, we have as associated one symbol, that is A, B, and C. And you can see here one more important thing: there is no final state. There is no final state. The only the initial state is there, but there is no final state. Why? Because we need not to have any final state, because we are not checking the validity of something, or we are not trying to accept something or reject something. So whatever input is given, based on the input string or based on the length of input string, output is generated. So no need to have any final state. Now you can see, my friends, here. So if I represent this particular Murray machine in tabular form, then how we will do it? So let's see. So how many states are there? Three states are there: Q0, then Q1, and then Q2. And now you can see, my friends, here Q0 is the initial state, so we can have one arrow with this. So this is representing initial state. Now you can see here we have used two symbols as input, 0 and 1. In all these states, you can see only 0 and 1 input symbols are there. So we will have two transition here for 0 and for 1. And one more thing we will have here in Mealy and Murray machine, that would be the output. So that would be the output, or I can write it like this: output. Now you can see here, with each state we have mentioned one symbol there. So with Q0 we have mentioned A, so I'm writing Q0 A here. Q1 B is there. So with Q2 C is there, so I'm writing like this. So this would be in the tabular representation of this machine. Now I will write some transition, how we will write transition here. So now you can see, my friend, on Q0, if we are getting 0, so we are staying on Q0. We are staying on Q0. On Q0, if we are getting 1, so we are moving to Q1. On Q1, if we are getting 0, so we are moving to Q2. On Q1, if we are getting 1, so we are staying on Q1. On Q2, if we are getting 0, we are staying on Q2. On Q2, if we are getting 1, so we are again staying on Q2 itself. So this would be the table of this particular Murray machine. So I hope this would be very much clear how to create tabular representation for this. Now I will tell you one example how this machine will generate the output. So you can see, my friend, in any machine, if we are not giving any output, so it will still be in fine initial state. It will still be in initial state. So it will always generate the symbol associated with initial state. So suppose I will give you this any one example input here as 0101. This is your input 0101, and now you can see here the initial state is q0. So we are on q0. We are on q0, and whichever state the machine is, in whichever state the machine is, it will generate the output symbol associated with this state as output. So as it is in q0, as it is on q0, so it will generate symbol a there. It will generate a symbol a there. Now we are on q0 and we are reading 0. We are on q0 and we are reading 0. So we can see in the transition table on q0 if we are getting 0, so we will again stay on q0. And now as we are again moving to q0, so it will generate one more a. One more a. Now we are on q0 and we are reading 1. We are on q0 and we are reading 1. So on q0 if we are reading 1, so we will move to q1. So here we will move to q1 and it will generate the symbol as output which is associated with q1, so it is b, so it will generate one b there. Now we are on q1 and we are reading 0. We are on q1 and we are reading 0. So we are on q1 and we are reading 0, so we will move to q2. And then it will generate output symbol associated with q2, so which is c, so it will generate one c here. Now we are on q2, or we are getting 1. So we are on q2 and we are getting 1, so we will stay on q2. And as we are staying on q2, so again we will generate associated output associated with q2, so that is c. So in this way, now string is completed. So this is the final output of this machine. Now you can notice one thing, friends. The number of symbols in the input are 4, but the number of output symbols are 5. So similarly, if you increase one more symbol here, so output also one more symbol will be increased. So that means for n number of symbols, for n number of input symbols, Moore machine generates n plus 1 number of output symbols. N plus 1 number of output symbols. So this is very important thing and very important fact about Moore machine, because it is commonly asked in any competitive exams as a MCQ question, or in your university exam, or any internal component you can have this questions. So this is very important fact about Moore machine, that for n number of input symbols it generates n plus 1 number of output symbols. So I hope, friends, it would be very clear to all of you. And now, if you have any doubt, any query, you can always write to me in comments. I will definitely reply your comments. Thank you. Thank you so much.